Hi, good evening, everyone. My name is Jessica Storm. I'm a forecaster here at the National Weather Service in Burlington, Vermont. I have Seth Kudikoff here with me as well. He's another forecaster at BTV. And for this webinar, we're going to be discussing the Pi Day Noreaster from last month, March 14th and 15th. This nor'easter, as I'm sure many of you remember, it brought a significant amount of snowfall to our forecast area, which we've outlined some of the totals here. More southern mountainous areas received the most snow, over 30 inches in a lot of these spots. Moriah had the highest snowfall total of our forecast area with about 36 inches. But on the Vermont side, we also had Ludlow came in second. In addition to some of these snowfall winners, if you will, we also have some notes from COCORA's observers describing some epic snow that they got. This really was a significant snowfall event. But of course, it didn't just impact our forecast area, which is most of Vermont and northern New York. It also impacted a lot of the Northeast. You can see kind of the bullseyes around the Adirondacks, Catskills, southern Vermont, western Massachusetts, Reedsboro, Vermont, which is actually in the Albany National Weather Service office's forecast area, had an impressive 42 inches of snow, and then West Brattleboro, not too far behind that. So I'll start off kind of with a summary of how this storm occurred, developed. We'll be discussing the coastal low kind of pictured here, how it provided 2-inch per hour snow rates. We also had some intense gusts with this storm, up to 50 miles per hour, which combined with how wet and heavy the snow was, it caused quite a few power outages across our area. The valleys were some of the most challenging spots from a forecast perspective. So we'll also kind of talk about how the marginal temperatures, the temperatures that are pretty close to freezing but not quite, can make a very difficult forecast. We'll also show you some models, describe how they did or didn't capture some of the features like the mesoscale band that caused the very heavy rates. And played a big part in kind of outdoing our forecast, overperforming, and caused some of the warnings issued throughout the day in places that we didn't previously have them or expect them. And then we have the Champlain Valley, Northeast Kingdom. Those are some acronyms we might be using throughout this presentation. So yeah, we'll kind of go through a lot of the features that we look at when we're forecasting and how things played out with this storm in particular. So an ensemble weather forecast is essentially, it's a set of forecasts that present a range of future weather possibilities. There's multiple simulations run, different variations, and so we'll kind of go over what we were seeing on these ensemble forecasts. There was a little bit of actually hinting at where some of the heaviest snow could set up, though as you can see, this underdid some of the snowfall in certain spots, especially in northern areas. This is the European ensemble, and it indicates the probability of snow greater than 6 inches. So there's a faint signal of deformation snow northwest of the pivot area of the storm out in southern Vermont. And this was indeed some of the area that got some of the heaviest snow. This is the Canadian ensemble. We noticed throughout this forecasting process that the Canadian was particularly bullish with this event, which looking back, it may have been onto something. It indicated essentially at least 10% chance of more than 6 inches of snow everywhere except for the St. Lawrence Valley. So it was really kind of insisting that there's a chance that there could be at least 6 inches. And then this is the American model called the GFS, and it indicates some heavy snow and points out some of the banding, the heavy snow band. But not only is it a little bit underdone in some places, it's also very late in the game. And the models tend to kind of evolve throughout the forecasting process. There's different runs each day. So that's why we're kind of always encouraging people to check back on our latest forecast. The data is changing and evolving, and we're just kind of making our best forecast with what we have at the moment. So this is kind of to show what a large uncertainty there was with some of the snowfall amounts of this storm. We felt pretty good about that somewhere would get pretty clobbered by snow, but it was difficult to determine exactly where that would be. And it's difficult also to kind of convey this to a lot of the public. Often, you know, we all kind of want that very specific, like 3 inches. You know, it's a very helpful definitive number, but when we have ranges like that, it's very hard to pin down such a specific number. Amounts could be anywhere from 2 to 12 inches for some of these spots. With this uncertainty, we kind of looked into other factors as well, like with this storm occurring in mid-March, temperatures were expected to be so mild. So we tend to lean on the lower end. As you can see, the little squares kind of showed where our forecasts were on these ranges. Because this warmer air can kind of limit the snowfall amounts. Unfortunately, we weren't anticipating the extremely heavy snowfall rates with that band that we'll talk about later a little bit more, and it brought temperatures down to that marginal just above freezing level, resulting in much more snow than forecast. And here's kind of another look on low end versus high end snowfall forecasts, kind of showing the challenge to pick a single number, and how sometimes it's much more useful to talk in probabilities, like the percent chance of exceeding a certain amount of snow is kind of an alternative way to display it. So convection allowing models, CAMs, we'll be looking at in particular the HREF model. So it's showing here the 24-hour snowfall ensemble mean. So those colors kind of correspond to the model's prediction of how much will fall over 24 hours. And as you can see, it's got some very high amounts in the mountains, but areas like the Champlain Valley have 6 inches at most. So this is kind of a first guess, the best agreement among the models. And this map is almost identical. I can kind of go back and forth between them, and there's very little change. This is actually the model's more worst case scenario. This is something that kind of indicates that since the first guess and the worst case are very close, it was a kind of a subtle sign that the event would overperform as it did. And this is the ensemble max for the model. This is the worst case scenario overall. It's still a little bit closer to reality, the high amounts that we did receive, but it is still underdone in a lot of places. This is kind of a similar map, but it's for hourly snowfall rates. So the amount of snow that fell in an hour, and you can see this model was really highlighting the mountains, but ignoring the higher amounts in the valleys. And this is the probability of more than 1 inch per hour snowfall. And once again, it keys in on those higher amounts in the mountains, where we did have our highest snow totals, but it lacks the high snowfall rates that did occur in some of the valleys that caused the overperforming. And this one even more kind of highlights the idea that we knew somewhere would probably get just kind of dumped on with snow, but we couldn't quite pinpoint where. This particular model has it pretty good in that kind of southern Vermont into Massachusetts area, kind of into the Adirondacks, but it did miss out on the fact that the 2 inch per hour snowfall rates were in a much wider area than this. And it's essentially how those the snow overcame the cold, the marginal temperatures. So kind of moving into messaging and social media, I wanted to show our hazardous weather outlook page on weather.gov to kind of show that we were highlighting the risk for snow and wind, snow being the biggest threat, especially southern Vermont. It's kind of another way to convey what's going to happen without pinpointing an exact number, because as I showed you, the ranges were so wide, but we knew that there could be some impacts. And this is what this kind of conveys with those extreme impacts in the southern greens. Of course, it probably could have been a little bit of a higher level of risk level in some of like the Champlain Valley, where we have like limited to elevated, where it might have been a little bit more than that. So despite the uncertainty, we wanted to start messaging what we were thinking and kind of give people the heads up that something was going to happen. We have this % chance of 6 inches snow or more, so that's kind of where what I showed you earlier with those percents, those probabilities kind of play into ways that people can understand that, yes, we are forecasting 1 to 2 inches in a place like Burlington, but there's 53% chance it could be much more than that. So when it's difficult to pin down a specific number, it can be beneficial to kind of talk about the percents. And we continued to kind of update on social media as we got new information, new data. That late to the game ensemble showed up. So we were kind of updating as soon as we got information. And here's a much more deterministic way of communicating our forecast. As you can see, there is a specific number put in for different times, for different snow amounts and wind gust forecasts, which is helpful in some ways, and also kind of puts us in a box with the single forecast numbers. I do think that this message was very important with the wind, especially because, like I mentioned, those gusty winds, in addition to the snow, caused some power outages, and we hadn't seen that in previous social media posts being messaged. And then here we have some social media posts for getting snow reports. These real-time snow reports, ground truth is kind of what we call it, can really help change direction or get more on track with the reality of the situation, especially with this event that had so much forecast uncertainty. And you can see we're kind of posting where we're expanding those advisories, those warnings, as the day went on and the storm overperformed. So at this point, we're kind of nowcasting, providing updates. So as we'll talk about how the storm unfolded, Seth will kind of discuss that.
All right, thank you, Jess. So now I'll move on to some of the meteorology of the event. As you can see in this beautiful water vapor loop combined with radar data over a 2-day period from 8 a.m. Monday to 8 a.m. Wednesday. Basically, this is a classic nor'easter emerging off the coast. And one of the challenges of why this forecast was so difficult is because the storm is actually developing well off into the Atlantic before it gets wrapped back to the northwest. And so the pinpointing how the snowfall on the northwest flank of the storm, first of all, it's nothing you can track until, because it is developing over time. You kind of have, as Jess said, we have to now cast the evolution of the storm. So in this loop, you can see precipitation pushing northward and then wrapping around as this storm intensified into the day on Tuesday, and then the wraparound precipitation on Wednesday. So zooming in now, a snapshot here for Tuesday morning when we had our biggest impacts with the heavy snowfall. You can see in this map, there is plotted here, we have what is called frontogenesis. So basically a front that exists up in the atmosphere a few thousand feet, and basically where the temperature changes rapidly with height in temperature range that is supportive of heavy snow. We see these bands develop, and in this case, across central Vermont, highlighted in the purple, is where at between roughly 9 and 10 a.m. the heavy snowfall was occurring, in which we had reports of a 3 inch per hour rate in southern Vermont for a co-op observer. And that type of snowfall, of course, is what wound up being the big player for where we received quite a bit of heavy wet snow during that time frame Tuesday morning. And zooming in now on radar, that loop I'm referring to with regards to the heavy snowfall band, you can see as it pivots to the west over time, so through central Vermont and then into the Champlain Valley of Vermont and New York. So one of the challenges was how far north and west this would go, and there is a sharp cutoff in far northwestern Vermont. The heavy snow band did not make it, so it's always a game of inches basically with regards to these heavy snowfall bands. There will be winners and losers. In this case, we wound up seeing a lot of winners. And then we zoom in now to what we look at for a forecast sounding for a specific location, what the temperature and humidity looked like, as well as the upward motion. So basically, this is a sounding for the J Peak area Tuesday morning that will show a forecaster some of those highlights that I mentioned with regards to that frontogenesis and the snow prediction from this one model. It played out pretty well. Again, this is kind of in that window where we're now casting. The event is ongoing, and we're getting into that sense of, okay, this is happening, and so we're going to update our forecast accordingly. And so this is the look at what we ahead of time, and we can message the possibility of a mesoscale band, even if we don't know exactly where it will be. There are rules of thumb based off of the synoptic meteorology. In the upper left of this graphic, you can see that typically when there's a low pressure area like this, a nor'easter, there is a pivoting band on that northwest flank, which is what we saw with this event. And again, because of the time of year and the temperature prediction being above freezing, basically near the ground, you had to get very heavy snowfall to overcome that warm air, and that's what we saw. Here's another look. Now we're going to take a trek through the surface pressure analysis as the storm evolved. So this was Monday night, as I've said. Monday night into Tuesday is where the low pressure area was well off the coast, and over time it strengthens. So it's the lowest pressure was 996 millibars that evening, and then we're moving 3 hours later, it's down to 990 millibars as it continues to move northward and a little bit east actually. However, at the same time, you can see that the second area of low pressure that was analyzed near Long Island, and this relatively unusual dual low setup basically was what allowed it to be a stretched area of low pressure that helped to increase the moisture. Basically, we had precipitation during this time frame gradually spread northward through Vermont, but the real heavy snow was going to be developing again on that northwest flank of the nor'easter as it was pulled back to the northwest at 5 a.m. You can see the two lows are pretty strong, but by 8 a.m. now the focus is on a deeper low that is again wrapped to the northwest, and so the general idea is that it follows the Gulf Stream, and so that intensifies the area of low pressure, and because of its elongated nature, it was able to have a broader area of snowfall as what wound up happening than what could in other cases be a tighter area with the sharper northwest cutoff, which is something that forecasters were dealing with the leading up to the event in the 3 to 5 day window, when it was not apparent that we would see the heavy snowfall in northern Vermont and northern New York, basically the way it played out. Then this is a way of looking at it. If I back up here, we've got ourselves that look at 9 a.m. And this is how the low pressure area, again, along with radar data, you can see overlaid that faint band of heavy precipitation is starting to get going. And the question was how far north and west it would go. And of course, the combination of the heavy snow and increasing winds associated with that strengthening low pressure area, the pressure gradient drives that strong northerly wind. And we did see quite a few power outages initially where the heavy snow in eastern Vermont was set up. That's where we saw the initial easterly component be strong, and then we wound up shifting into a northerly component on day 2 of the event. As you can see, the circulation of the storm on the western flank of the Noreaster on Tuesday night into Wednesday, we had additional lighter snow, primarily in the mountainous areas of central and northeastern Vermont, while we saw gustier winds down the Champlain Valley, which added to some additional power outages during that time frame. And then thought it'd be interesting to compare how this played out to a nor'easter that occurred 5 years earlier in a winter in which there was quite a series of nor'easters. And so in that case, we also had the challenges of how much snow would fall based off of the marginal temperatures of that same time frame. And in this case, we were messaging the expected snowfall being over a long period of time, and that snowfall rates would be relatively manageable. And as it turned out, we got reports of heavy snowfall, and that overcame what we indicated as being relatively light enough during the daytime hours where snowfall rates would not be heavy enough to cause travel issues. So this is always something we would like to do a better job of considering in the future, that there is, as just indicated, we do deal in probabilities. And so even though the most likely outcome in our forecast was conveyed with our watches and warning products, there are these situations, especially in the challenging late winter period, where we do see that worst case scenario kind of idea play out. And this is this snowfall reported map. Again, the idea of overperforming with 1 foot to 2 foot amounts getting into the valley locations is something that played out in that nor'easter as well. And so this was a comparison. If I go back here, both snowfall events were quite extensive with heavy snowfall across our region. And that is a final summary going back to how the snowfall played out with our snowfall reports for this event, with the widespread 1 to 2 feet, and then the locally heavier amounts across our southern areas and across eastern Vermont. Zooming back out, you can also see again that this was a remarkably large area of 1 foot plus of snowfall, especially in a winter that otherwise saw pretty few heavy snowfall events. So we did see the 1 to 3 feet heavy wet snowfall occur, which led to extensive power outages. And our main focus in terms of the learning experience and trying to convey the challenge of this snowfall event was with that heavy snowfall rate idea that we wound up seeing in a mesoscale band, which led to those heavier amounts on that end of what we were looking at for possibilities across the Northeast Kingdom of Vermont into the Champlain Valley. And this was a rapidly intensifying storm, and that led to strong winds, and that led to the hydrology and tree damage that occurred. At this point, we are going to be looking forward to answering any of questions you may have about this event. Thanks very much for listening.
And if you want us to go back to any parts and go over them again, just let us know. Any questions, welcome.
Okay, thank you, Adam. We have a question about, do you have a storm total map that includes a wraparound? I believe it would be the 16th or 17th. I believe that when we showed the initial slide all the way in the beginning, that should be a total snowfall for the event, which includes the wraparound. So that is why some of the amounts are quite a bit higher. So in the very beginning, I believe this does include that 14th through 16th. This should include. This was what we consider to be our final public information statement that we use to verify events for a storm total. So I believe up in Greensboro, the 18.5 inch should be, but we can double check on that. Thanks for the question. So this is a really interesting follow-up from Adam. Yes, the nature of marginal temperature and elevation means that we saw many situations where, although there was heavy snow in the valleys, the very, very heavy snowfall amounts in excess of 2 feet tended to be at higher elevation in such a way that location that could be only a couple of miles apart could see dramatically different snowfall amounts. So that was, again, with regards to why this is such a challenging forecast for meteorologists, even those that are quite seasoned here at BTV, in relation to just the elevation dependence of the snowfall amounts. And so we did indeed see the really high amounts in excess of 2 feet be tied to elevations generally above 1,500 feet and higher. All right, there's another question from Kate. Thanks so much. What are some first steps in improving the models for future forecasts? Also, are there pointed reasons why one ensemble in the collection you showed would better predict snowfall during this type of storm than another? Those are great questions. I'll do my best to answer. So as operational forecasters, we do rely on these models for sure to help guide our forecasts. And so the folks who work in the modeling field, they are basically, there's a combination of factors that they're going to be looking at, including verification of events that we experienced. In terms of the improvements, basically, it's hard to pinpoint what would be done specifically with regards to snowfall forecasts, in part because they tie into many variables such as the precipitation amounts, the temperatures, and snow ratio, and so on. So I would say that the first steps would be with regards to improving model physics, and especially in the near the surface, and basically capturing what is going on in terms of verifying the ground truth in these events where the basically you are seeing the boundary layer, what temperatures lead to snowfall, for instance, versus rain. The sensitivity, basically, that a modeler would be testing with regards to future improvements. And then in terms of the ensemble, basically what we laid out were 3 large ensemble groups from different large modeling entities, with including the North American GFS ensemble. So I would say that we don't necessarily have a preference for a single ensemble. That's why we do look at all 3. It's a good question, though, with regards to if there is any one that tends to perform better with regards to snowfall amounts, or over, basically we can do studies to look at over a particular period of time. So like a lead time of, say, 3 days, if you were to verify, for instance, the mean forecast of an ensemble, that would be maybe a way that we could in the future have some quantitative assessment. We could assess maybe if there's a particular ensemble that could predict snowfall better. But at this time, I would not say that a forecaster could necessarily prefer one versus the other. It'd be more looking at the meteorology, what individual trend, basically, that the model is showing, if they fit with what basically a forecaster can assess as being the most likely scenario. All right, are there any more questions? We're happy to take anything in the chat. Thanks so much for joining, and those who have asked questions so far, much appreciated. Okay, there's a question about a map showing surface temperatures and or wet bulb at the storm onset. That's a wonderful question that we did not show that. That would be a good thing to, for sure. I know here in Burlington, we did see precipitation begin as rain early in the event and with temperatures in the mid 30s. And then we did see some colder air, just enough move into the area such that temperatures fell to 34. And that was cold enough for precipitation to be in the form of snow. And that was pretty common, that the surface temperature and dew point. And so basically we did see those wet bulb temperatures just low enough to cool to what was enough to see snow as opposed to rain, despite being above freezing. All right, well, give it another couple of minutes. If there's any additional question, we'll be happy to take. Not, thanks so much for attending.
And we'll be posting this on the YouTube later, so you can rewatch it if needed. Have a good evening, everyone. We're gonna close out this presentation. Thank you for coming.